When you look at an active OLED screen or a solar panel, the performance you experience is dictated by what happens at the nanoscale. If we zoom past the active layers, we eventually hit a boundary where two dissimilar materials meet. This interface is the primary choke point in modern solid-state devices. To create light, electrons have to cross from a metal electrode into an organic semiconductor. If the energy levels of these materials do not naturally align, electrons face severe contact resistance. You end up pumping excess electrical voltage into the device just to force carriers across that boundary, wasting power as heat instead of generating light. This diagram maps the problem. Between the metal's Fermi level and the semiconductor's LUMO, there is a steep vertical gap. We call this the electron injection barrier, an energy cliff an electron must scale. You cannot simply swap out the semiconductor to fix this alignment. Altering the chemical structure of the light-emitting layer usually destroys the precise color or efficiency it was designed for. Solving device efficiency doesn't require inventing new bulk materials. It requires re-engineering the atomic surface where the materials touch. The parameter that governs how easily an electron leaves an electrode is the work function. The work function, phi, is the energy cost to lift an electron from the Fermi level to the vacuum level. A large work function means the Fermi level is buried deep, requiring high extraction energy. A small work function means electrons sit closer. Because this value relies on the vacuum level directly outside the material, it is not a fixed constant. It is highly sensitive to the exact state of the surface. A pristine metal electrode alters its work function when exposed to oxygen, humidity, or ambient air. That sensitivity gives us our engineering lever. Work function modification is energy level engineering at a surface. By deliberately altering the surface condition, we shift the effective Fermi level relative to vacuum, controlling exactly how charges cross the interface. To manipulate these barriers accurately, we have to separate the work function from the intrinsic properties of the semiconductor. This matrix outlines the strict definitions we use to diagnose energy cliffs. First, work function is distinct from ionization energy. Look at the origin of the arrows. The work function originates at the Fermi level. Ionization energy originates at the highest occupied molecular orbital, or HOMO. Similarly, the work function is distinct from electron affinity, which measures the distance from the LUMO to the vacuum level. When an electrode and a semiconductor are brought into contact, their vacuum levels automatically align. They lock together, creating a continuous reference frame across the device. That mathematical alignment dictates the barrier. If the metal's work function does not line up with the semiconductor's electron affinity, the built-in energy cliff is locked into place. The semiconductor's electron affinity and ionization energy are fixed properties. The only variable we can control to bridge that gap is the surface potential of the electrode itself. We control that potential using a specific toolkit of surface treatments. Depending on the device, engineers might use thin interfacial oxides, control charge transfer, or apply self-assembled molecular monolayers. Regardless of the specific treatment, the primary mechanism at work here is the creation of a surface dipole. Look at this baseline energy diagram for a bare metal surface. Before any treatment, the vacuum level extends as a flat, continuous line extending outward from the material. Now, we apply a dense molecular layer to that surface. By stacking positive charge directly over negative charge, we physically separate the charge distribution at the atomic level. This charge separation forces the vacuum level to jump. As an electron attempts to leave the material, it hits this localized electric field, experiencing an abrupt electrostatic step in the vacuum energy, right at the boundary. The bulk metal underneath hasn't changed. The Fermi level remains exactly where it was, but from the perspective of an approaching electron, the apparent work function has shifted. The size of this shift is predictable. It depends on n, the density of the dipoles per unit area, multiplied by the perpendicular dipole moment. Pack more aligned molecules onto the surface, and you generate a larger shift. By pointing these molecular dipoles either inward or outward, we synthesize an effective work function precisely tailored to the device's needs. Let's run the numbers on a real interface. On the left, we have an untreated metal electrode with a work function of 4.3 electron volts, facing an organic material with an electron affinity of 3.2. The vacuum levels align, and the arithmetic reveals a large 1.1 electron volt barrier for any electron trying to enter the LUMO. To fix this, we apply an interlay that establishes a negative dipole. This shifts the effective work function of the electrode down by 0.8 electron volts, bringing it to 3.5. Recalculate the barrier, and the 1.1 gap shrinks to a highly efficient 0.3 electron volts. This establishes a definitive rule for device design. Synthesizing a low effective work function smooths the path for electron injection. Synthesizing a high effective work function assists hole injection. By aligning the effective Fermi level directly with the target molecular orbital, we reduce contact resistance and save operational voltage. The textbook math assumes a 1-to-1 relationship. If you shift the surface potential by 1 electron volt, the injection barrier should shrink by exactly 1 electron volt. But an organic interface is not passive. As you drive the energy levels closer together, the interface actively pushes back, a phenomenon called Fermi level pinning. Notice the springs in this model. They represent interface resistance partially canceling the engineered shift. That resistance comes from the messy reality of the interface. Forcing the materials together can trigger chemical reactions with the electrode, induce disorder states in the molecular structure, or create new charge transfer states that generate opposing dipoles. Because the interface responds dynamically, you encounter diminishing returns. Adding a denser dipole layer yields weaker results once pinning sets in. Modifying the work function is an attempt to command the energy levels, but the chemistry of the interface always dictates the final alignment. Because of pinning and the risk of contamination, theoretical calculations are never enough. The shift must be measured directly. This diagram outlines 2 ways we verify our engineering. First, the Kelvin probe. This is a non-destructive tool used for relative measurements, tracking changes to the surface work function in real time. Second, ultraviolet photoelectron spectroscopy, or UPS. This uses photons to eject electrons from the sample, allowing researchers to measure the absolute work function and ionization levels. Those measurements translate to direct hardware improvements. In OLEDs, confirming the exact surface shift means minimizing the voltage wasted just trying to get current into the device. In solar cells, tuning the interface creates selective contacts. We dial in a barrier that allows one carrier type to exit while actively blocking the other. This master data table summarizes the architecture. The work function sets your baseline. The interface dipoles provide the mechanism, and Fermi level pinning represents the physical limit of the engineering. We cannot reinvent the bulk chemistry of semiconductors every time we need a more efficient pixel or cell. Instead, we engineer the vacuum level. By manipulating that microscopic boundary, we dictate exactly how charge moves, translating nanoscale potential into real-world performance.